for bar magnets. The purpose of this lab is to find the experimental distance dependence of a magnetic field of a bar magnet in order to find the experimental magnetic dipole moment, and then to compare the experimental off-axis magnetic field to the computational magnetic field. The dipole moment that was calculated was 3.09444, and then you can see the experimental computational magnetic fields, with the experimental one being about twice the size of the computational one, which will be discussed later in the lab. For the fundamental principles and models used, the magnetic field of a dipole can be simplified to these first two equations that we see here for the distance-dependent equations, where different data points can be graphed in order to find n in the first equation, and using the second equation, which will then be plugged into the third equation, the b-axis equation, in order to calculate the magnetic dipole moment when it is rearranged to find it. For the computational model, the Biot-Savart's law is used because it's a little bit more complicated and it's a little bit more difficult to be done by hand, so this is used to find that. For the experimental model, the system was the bar magnet, surroundings was Earth and everything else, and for the initial conditions, the bar magnet is lined up at several locations, so it's perpendicular to the Earth's magnetic field. That way, when we see the X component of the magnetic field, we know that's only coming from the bar magnet and not the Earth. So for the details of this, the magnet is lined up at several different R-value locations, as we discussed a minute ago, and its magnetic field is recorded. This is, when graphed, this is used to find the n value of 2.2964, or negative 2.2964, forgot the negative there, as we can see in the graph, and an LNK value of negative 13.23. We plug these values in at R of 0.22 m, which was chosen arbitrarily, into the first equation at the bottom, and then we find the magnetic dipole moment using the third equation. The second equation is what is the equation in the graph. A similar process is then followed in order to get the axis measurement and then to calculate the experimental magnetic field that I list here. Here's the computational model. As you can see, this is all the parts of the model that I had to edit on the left and middle sections. That's all the code. And on the right is you can see the final result. At the bottom, you can see 1.4659 times 10 to the negative fifth is the magnitude that is computationally found. This is half the size of the calculated one that we did earlier from our experimental data. So the experimental data is showing a stronger magnetic field than what is found in the code. This probably came from some errors that are skewing the experimental data, since the code is using a much more complicated model. So it is more likely that the experimental data is a little bit messed up somehow. So some of the errors that could contribute to this, as I mentioned, is not perfectly lining up with the Earth's axis. So that part of the Earth's magnetic field is contributing to the magnetic field that we found. So it's actually a superpositioned version of the magnetic field. We're looking at the net instead of just the bar magnet, which would make the magnetic field of the bar seem a little bit bigger than it's supposed to be. The meter stick is also not super precise to find the R value, so that can mess it up. And the experimental equations from over here, as we see, make a lot of approximations in order to do that, and they're not necessarily as accurate as the computational model. So for the discussions questions that I mentioned needing to show, it's true, false, false, and true, as it can just be seen by doing the experiment and by looking at the different equations. You can see that these are all true and false. So for the discussion questions, if we orient the setup so it's the Earth's magnetic field is anywhere besides the y-axis, then the magnetic field that we record is going to be superpositioned version of both the bar magnet's magnetic field and the Earth's magnetic field. This would make the magnetic field we calculate too large because it's including a secondary magnetic field in there. So that was also one of the potential sources of error that I mentioned a minute ago. And if we redid the experiment with two magnets, the magnetic field would increase. It's kind of similarly how increasing separation distance of electric dipole would increase that strength, because it would become one larger magnet rather than two small magnets. The direction would not change though, because the direction of the north and south will still be the same, and the observation locations have not changed. Thank you for watching.